Hello, hello there. Welcome back. My name is Al, and this here is lesson 104, I guess, in our series, mainly to do with C++. But right now we're looking at Windows security features, and in order to do that, I've gone on to a discussion about Windows synchronization objects, which is something that needs to be covered first, at least in my case. Now I do have something to add here this time, even though I haven't made any bouncing balls yet. And so I just thought I'd let you have a look at this thing here, which I'm just going to fix this up a little bit. I have a function that returns a random number within a range, inclusive, and but it turns out that for the new object that I'm going to tell you about, I need to use large integers, and so I had to add a 64-bit version of my random range, which is not hard. It's basically a template. Is that the only place? Okay, so now it took me a while to get this going, in fact. And it's good to actually to do these sorts of experiments. You know, before I had a blue screen, right? Well, I thought what I wanted to do was to first make a separate thread for that main window, and then maybe do something else in WinMain here, which I did. I was drawing dots. Well, I had two questions in mind. One was, I pretty much knew the answer. These memory device contexts, can I draw to them from a different thread, and then will it work? And the answer to that is, of course, yes. However, if you try to draw to the window HDC, that's always going to fail. You can only draw to that HDC when you get a WM paint message, and that has to be in the Windows thread and thread context, and you have to call a special function and so on and so forth. But okay, so that's fine. I can get the Windows memory device context, but then that's a shared resource. So initially I had created a critical section object, or I made this thing into a locked critical section locked object, and in order to acquire that thing, I used the macro that I had and so on and so forth, but I kept getting these crashes. And I guess the reason was essentially because what I had to do first was I had to be able to acquire the window itself in order to get some data out of it. But the way I've done it is, maybe I shouldn't have, but I have no default constructor for those window things. So I had to make a pointer, and so therefore I had to make it a smart pointer. And so the window thing, wherever it is an H window, right? Which initially was a global and now I made it static global. And when I when I begin the thread, I just make a new. Done. I knew it in the thread prop. First, create the atom, then make a new window out of the atom, and then set the global. Oh, that sets the global. So now there are things that are counting the window, deciding whether or not to delete it, right? But the window itself also contains, turns out, well, you saw one of these handle to TLS divs, which is also a smart pointer type thing, right? And then I put a locked, MX locked thing around this, right? And so here we got all these various counters, and they will get out of sync, essentially. The window would decide to destroy itself, right? And but still, there was a lock on the critical section for the div and so on. So it was too complicated. It was too complicated to do it that way. So I figured that basically I can just make a separate critical section for the main window. And where is that created? Critical section main window. Oh, here's declared here. This object creates it in its constructor. Okay. And I also kept running into problems with getting deadlocks. Things like deadlocks, because what could happen is the window quits, and one of those other things is waiting to waiting to enter this critical section, which is locked, right? And well, actually, it wasn't really a deadlock, but it turned out the reason for the other thread finally acquiring the critical section was that the window was dead, right? And then at that point, it was trying to access stuff in the window. And again, too much complication. That critical section is locked during WM paint because I need it, right, at that point. And so if it's acquired, the window can't paint itself. And then during quit, another thread might not know about that, and it might acquire the HDC thing, which is going to die, and so on and so forth. And so I realized, therefore, what I got to do is, if I'm going to quit the program, I'm going to lock the access to the main window completely. So if anyone wants to access the main window, they're out of luck, right? And when the main window is finally been deleted, then I unlock it. Now they can access the main window, but of course it will be deleted. So instead of using lock and unlock, I added a new function which says try lock, okay, and so that allows you to just test to see. It's like the mutex thing, wait 0. if you call try, that is what wait 0 is for a mutex, essentially. If you call this function, it returns immediately with either true or false. And if it returns true, then that means that you've acquired the critical section, and you can go ahead and do whatever you want. Otherwise, if it returns false, then you didn't acquire it, and so then you've got to go back to doing something else. So what that allows me to do then is to lock. So lock the critical section during the deletion, the closing down process, right? And then anyone who tries to acquire the critical section immediately, not blocking or anything. So now it doesn't say that here, but lock main window here returns null if that try fails. Now here I say continue. Okay. Now the main window thread may still be active, and it might come back down here. And so again, I have another problem. These things aren't going to quit. They should be quitting, right? But the main Windows thread isn't actually dead yet. So I invented a new event which says that the program's terminating, and so that allows you to check to see if that signal is set and then quit. This guy can quit. Now, initially I was running this thing around, and it was using up a lot of CPU. In fact, almost the entire CPU resource. And the reason was because I was just doing the simple thing of using my once every such and so, do your thing. So then I tried putting some sleeps, and that helped a little bit. And then I remembered, I was sure that there's some kind of event that has the properties of a timer, right? Like a ticker. And sure enough, there is, and it's called a Waitable Timer. And here, there's two forms of it. Well, it's like these other things, other types of events. The first part is a security descriptor, which is always null. Now, these say exactly the same thing. This should be, one of them should be true and one false. If you look at the help here, manual, okay. Now, what happens is you create one of these things, okay, and it can either be a manual type or an auto type. If manual is true, then you have to reset after it gets after the timer gets notified. You have to reset it yourself. Otherwise, the time, I don't know why they don't just say otherwise. It resets itself automatically. Okay, so that's called a synchronization timer, apparently. And that was the kind I wanted to use. There was no reason for me to have to reset it, because I want to go back to doing it my wait, do another wait. And so just like the once every thing, I would randomly select a time. Now this is the main main thread. And so that allows it to become really efficient. After I made this change, it went from First it was about 99% CPU, and then 50%, and now 0. And it behaves now in the way that I expected it to. Originally it wasn't behaving. What I'm doing here is I'm adding, every now and again I'm adding a new thread, okay? And what the threads do is they randomly draw dots on the screen, okay, with a color. Initially with a random color, okay, a random color each time. But I thought, well, that's no good. I can't tell which thread is which, so each one will have its own color. Because I had a lot of threads here. And instead of where I was setting the color of the main window here at random, I moved that over into the Windows thread and discovered something that I noticed almost immediately, that the main window was always starting out with the same color. I have a thing here, rectangle random RGB, and this is supposed to generate a random RGB value. Okay. Now, these no longer have the meanings they originally had, but I wanted the background to be kind of a pure color, like CGA type colors, and the balls just random. I didn't like that. I didn't like some of the colors are just so ugly. I figured that you get a nicer color if you weight it more towards the blue. So this has more likely to be more blue, but it range. This is random bool, not random range. So this is either going to be 0 or half, or 180, whatever, or 0 to 255. Okay, so it is possible. Could be an ugly yellow, but it would be a dim ugly yellow. Okay. Now then I have dim and intensity basically. So this is the dimmer case, this is the intensity case, and the background colors look okay. But it was always starting out at the same color, which was an ugly color, it turned out. And then I realized something I should have realized, and that's why it's good to try these experiments, just fiddle around, because you start to notice things. Why was it always coming up with the same color? I checked common, I was calling srand, and then I realized, of course, srand, right? The rand function has to be thread safe, right? So that means that the seed has to be thread specific, right? That's a global variable. I mean, they could guard it with a mutex or something, but it turns out that instead of doing that, every thread gets its own seed, and so therefore I wasn't setting the seed. I wasn't seeding the random number generator in the new thread. So therefore, I learned that each thread is responsible for seeding their own random number generator. And so that's something new that I learned. The other thing is I learned about these waitable timers. And the advantage, of course, is not only that it's more efficient, but I can wait on that timer here, and the event which tells me the program is going to terminate. And if the reason is that the second event fires, then that means I'm going to get out of here and stop doing this. And for the dots, similar idea. If if the reason for the termination was the second event and break. And I still got this other thing, which is from those signal classes. I would like to have wait on this object as well, right? Well, I wouldn't even. Well, I would have liked to have been able to wait on all these handles, right? Instead of having to have this say quit, but I don't have a class. I can make, I can make this signal structure, but I can't get the timer in because that's a new thing, and I don't have a class for that. And the multiple waits, there are no multiple wait functions that involve timers in that set of classes that I have. Anyway, that's the long story. Now let me just run this thing so you can have a look and watch the. Now every 10 to 20 seconds I change the background color, and whenever that happens I spawn a new dot thread. Okay, each dot gets a random color. Each dot thread gets a random color. Okay, and that's any kind of color, and draws a circle of random radius at a random position somewhere on the screen, within 1 or 2 seconds. Okay, so you'll see how quickly, once this compiles, then that will build up into well, how many balls. At first it seems like it's nothing much is happening, but once it gets going, it really starts to fill up quick. Okay, so here we got our first, here's our first, the color of our first thread. Alright, it's hard on this background to see them. Okay, that looks like, oh yeah, this is a new thread. Okay, now you'll notice the CPU here should be, usage should be 0, which it is. Previously it was already, it'd be at 90%. Because a timer is just like any other event object, it costs nothing to wait. And this drawing is only drawing to the memory device context. Well, and then it tells the main window to update itself, but that's pretty quick. That's just a straight up blip. So you can see, I don't even know what the last new color was, but it runs pretty fast. You'll notice occasionally we'll get a miss on the a failed lock on the critical section for the device context, but it's rare. So you can see now with just hardly any thread, it's going pretty fast. And we got a lot of different colors going. Not that many. Well, there are as many different colors as there are threads. And we're not getting any problems accessing the critical section. Even with all this drawing, it's unlikely to get a collision. Because it's very efficient, it's very fast to draw these dots. Now, I don't know what the maximum number of threads is that I can create, but already we've got quite a lot going. all of these, see? It's like 10 or so. Now shutting down, there was a miss there. See, now there's enough that we're starting to get collisions. But not that much, really. Now the shutting down process was another tricky business to get right, to get everything to happen in the right order. And really that final lock and the extra signal to tell everybody to quit was what did it. There were a few threading related bugs, but they weren't actually that hard to track down and fix. Turns out, usually they're impossible to figure out, but this one was pretty easy. You can see it's nice. It's really going nice now. It might even fill up the screen by the time the next thread gets going. So there you go. There's an example of a whole bunch of threads all accessing a global resource using a critical section, a testable critical section, that's a try thing, and I'm going to hit escape to show you that everything should clean up properly. See? Nothing, no problem. All the threads exited fine, no memory leaks. And the reason is, of course, because I can wait on two things at the same time. Get up very quickly. Yeah, that solves all of my problems. It's basically this global signal to tell everybody to stop. Now, in the case of the dots, I have them in a list. I have a list of TAS. What was that? Thread and signal. That's what that meant. Each one is past that a nude pointer to a signal, which really is completely useless. Because the main reason why they split now is this global. I can probably get rid of this other one. And their handle. Now to kill all the threads, normally, and this part isn't even necessary anymore. By the time I get here, most of them have quit. And I was getting assertions here because they had they were deleting their own objects. They're not quitting because I'm setting that signal anymore. They're quitting because of just the global thing. Then I've got to go through and wait. I got to wait for those threads to quit. And I don't have that in the signal class either. What I need is a thread class, I'd like to do wait for multiple objects with a list of all those threads, but it turns out that a thread is always in this signal state, okay? So a wait 0, the thread's always signal, so you can't wait multiple objects in threads. But I could have added another signal, I guess, to all of the threads and then waited on that. Anyway, this works okay. I just keep going through the list, and eventually Normally you get a wait timeout, and that means that the thing's active, right? When I don't know what the other return value is, but if it's not wait timeout, then it's dead, and then I can remove that one from the list, delete its useless signal, and therefore kill off all those things. And so the order of shutting down, kill all the dots. Again, even though this signal has been fired, all that tells me is that the program is in the process. The window is in the process of terminating itself. It might still be cleaning things out. So we'll have to do another type of thing. Here again, I can't wait on a thread because I don't have any kind of thread class to wait on. I have to always do this type of comparison. This is a non-efficient thing, right? Like I can only test to see if it's still active. I want to be, if I make a thread class, I would make each thread automatically have a special signal that gets fired as soon as the thing has destroyed itself. That's what I plan to add. Thread. I have a thread class. I'll just copy what I have over, of course, each thread when it starts out, it's got to see, do srand and any other things I discover at random while playing around. Anyway, so now you know about another signal and a little bit about how to use it. One of the things you have to be aware of is that these times here are negative. And you have, for the waitable timer, the minus sign doesn't mean negative time. It's just a flag, and the flag means that this is relative time. Relative. This is in nanoseconds or something. Create waitable timer. Set waitable timer. Yeah, 100 nanosecond intervals. So it's very finely tuned time. Positive values indicate absolute time. Okay, and it has to, be sure that it's UTC based, blah blah blah. And so this is like if you're waiting for December 12th, 2014 at 7:30 or some specific time. Otherwise, if it's negative, then it's relative time, relative to your current time. So you have to put in a negative number, and it has to be, this value turns out to be 1 second. That's 1 million, right? 10 million. So value of 10 million is 1 second. Turns out, according to their example. I just took this example. They said waiting for 10 seconds, and I copied this number, and I dropped 1 0, and I decided that's 1 second. Okay? Alright, so that's that. Now I want to cause some, rather than just dots, I want to make some motion happen. I'm not sure how to do that without having to redraw the whole screen every time. But I think maybe I have some ideas. Okay. See you next time.